So we're on page 2 of our Ionic Bond study guide. Question number 18, why do atoms share electrons in covalent bonds? They share them so that they can have to form stable compounds. In the process of sharing their electrons, they achieve noble gas configuration. For example, you've got carbon dioxide. It'll have a double bond. Each of these lines is going to represent 2 electrons shared. The carbon believes that thinks it has 8 electrons around it. And let me draw these electrons over here to make it proper. And then oxygen thinks that it has 8 electrons around it, which it does, but they're just being shared. Each of these lines is representing a pair of electrons. Number 19, let's see. Draw the Lewis structures for the following structure for these. Well, we've practiced this quite a bit in class. And so here's the Lewis structure of these two. I'm just going to connect those together, and then there we have our oxygen bond. For chlorine, okay, chlorine is in group 7. So there's its 7 valence electrons. I'm going to draw another chlorine here. I'll do its electrons in a darker color, but 1, 2, 3, 4, 5, 6, 7. And then right here, these two share. So that's for chlorine. Nitrogen is in group 5. So when we draw its structure like this, I'll draw the other nitrogen over here. Let's see, I'll use a different color for it. And actually, I'll use different color open circles to represent nitrogen. So what happens is these two connect together as a covalent bond. These two form a covalent bond, and these two. So we end up with a triple bond, very strong. That's for nitrogen. The Lewis structure for calcium. Actually, here's oxygen. Sorry, skip to oxygen. For oxygen 2-, so the regular Lewis structure for oxygen is going to be like this. But this up here is saying this is the oxygen anion. So what's happened is it's gained 2 electrons, and because it's gained 2 electrons, it's going to have a -2 charge. So now it's got its 8 electrons. Sometimes we may draw brackets around it to let us know that we've modified it. For calcium, calcium would normally have 2 electrons out there in its outer shell, but it ionizes, it loses those. So when it loses those 2 electrons, gives them away, it's going to now have a +2 charge because it's lost 2 negative charges. And so the Lewis structure for it will just be the symbol calcium with the +2. And similar for lithium. Lithium has 1 valence electron. It loses it. It gets rid of it. It doesn't want it. Now it thinks it's got the structure of helium, but the price that they pay is that now it has a +1 charge because lithium still has 3 protons in its nucleus, but now it only has its 2 electrons in its 1s orbital. Which of the following formulas represents an ionic compound? Well, ionic compounds are when you have a metal bonding to a nonmetal. So we have right here, we've got nonmetal and nonmetal. That's going to be covalent. Nitrogen and oxygen, both nonmetals. Barium is a metal. Oxygen is a nonmetal. Here's an ionic compound, and both of those are nonmetals, so that's going to be covalent. So we got 3 covalents, and then we have just 1 ionic bond. Which of the following formulas represents the biological molecular compound? It's going to be the C6H12O6. And the reason for that is that you've got carbon, hydrogen, and oxygen. Basically, the simple formula is CH2O to the N. You don't need to worry about that now. But this is basically sugar, and this is stored how plants store energy. But the biological is going to have carbon in it, and then it's going to have water in it too. Carbon and water, CH2O. Number 22. Which compounds are made from bonding? Molecular compounds, also known as covalent, are made from bonding metals to nonmetals. That's part of the definition of a covalent bond. And which of the following represents a molecular covalent bond? So for these bonds, it's going to be nonmetals bonding to nonmetals. So sulfur and oxygen, covalent. Beryllium is a metal and fluorine's a nonmetal. This one's ionic, covalent. And then zinc and oxygen, that's a metal bonding to a nonmetal. That's going to be ionic. So we just have one molecular bond over there. How does oxygen obey the octet rule when it goes to form compounds? Well, again, oxygen by itself, its Lewis structure looks like this, showing that it has 6 valence electrons. So what oxygen's going to do, it's going to share electrons with other atoms. So if it can find, let's say, in our friend water, if it can come along and find a water molecule, actually, let me take that back, if it finds some hydrogens, and I'm going to have to overlap here. Now we've got H2O, and it's formed the octet by sharing an electron with each of these 2 hydrogens. The question here is, under what conditions will potassium bromide conduct electricity? Potassium and bromine form an ionic bond. And ionic bonds, when they're in their solid state, when they're in the crystal, they won't conduct electricity. You have to melt them. When they're melted, they will conduct electricity, or if you can dissolve them in water. Because when you dissolve them in water or melt them, the electrons, the anions and the cations that make them up are going to be able to freely move back and forth. But when they're in a solid form, they're locked into a lattice pattern like this, and they can't get out of it unless you can add enough energy for it to break the bonds that hold them in place, the electrostatic bonds. So melting or dissolving will allow ionic compounds to conduct electricity. What is the charge of a sodium chloride as an ionic compound? As a compound, sodium chloride is neutral. If we could look inside of it, we'd see that it's made up of a sodium cation and a chloride anion. But together, they balance each other out into a neutral compound. Number 27, what causes a dipole interaction? And dipole, kind of think, okay, you've got a plus end and you've got a minus end. If we were, magnets are a dipole, they have a plus and a minus end. And so what causes this is the differences in electronegativity. And electronegativity is how strongly an atom wants to pull an electron away from another element. In class, we had the polar bear and penguin assignment. The big polar bears represented the very strong electronegative elements, and the penguins were the very small electronegative. And if you get those in a tug of war, the big one's going to win. So what happens is, for example, with the element hydrogen, which has a low electronegativity, and then the element fluorine, which has the highest, they're sharing electrons, but if I try to draw what's happening here, the electrons are spending most of their time around fluorine. Occasionally they'll come over there. So because the electrons from hydrogen come over here, this side tends to become a little bit negative. Not truly wholly negative like they do in ionic compounds. This side over here, because hydrogen is just a proton, and when you take away its electron, it becomes partially, and this is the Greek letter delta representing partially positive. We can also represent this with the arrow like that. So because the fluoride is hogging the electrons, it's going to tend to be a little more negative. And this causes what the dipole is now, if you have another polar molecule, this is a polar molecule, negative and positive, it's going to tend to, another hydrogen fluoride is going to be attracted like this, because this hydrogen is going to be attracted to the negative, and water molecules will do this. And so you can start to, in liquid, you can start to get these little interactions where you're getting hydrogen fluorides attracted to each other. It's almost, in a sense, kind of like we're building that crystal lattice we had with ionic compounds, but it's not as strong. Covalent bonds are made between which 2 types of elements? Between metals and nonmetals. What happens with electrons when an ionic bond forms? Well, with an ionic bond, what happens is you've got, again, I'm going to use our base friend sodium. It loses its electron to become stable. So you get this plus charge on it. That's the price sodium pays for having noble gas configuration. It's stable, but it has this plus charge. On the other side of the table, the nonmetals, chlorine, will gain an electron. So what happens now is these charges, they're opposite, they're going to attract. They're going to want to come towards each other, just like when you have a magnet and you put two north ends of a magnet, a north and a south end of a magnet together, they're going to attract. And so now they're going to be locked into this pattern near each other. They're going to get as close as they can until their electrons are so close that their negative charges of the electrons stop them from physically coming any closer. But you start to get then the repeating pattern. Another sodium atom can come over here, and then a chloride ion, and you start getting a crystal pattern formed. And let's see, metals form cations, and nonmetals form anions when they bond together. That's with ionic bonding. Question here is hydrogen, and when hydrogen forms a bond with a halogen, what type of covalent bond is formed? Well, hydrogen, again bonding with our friend fluorine, you're going to get a very polar molecule. Hydrogen has, the electronegativity, I don't have my chart in front of me. I want to say it's 2.1. I could be wrong. You've got your chart I gave you in class. Fluorine has an electronegativity of 4. When you subtract these, we get a difference of, let's see, is this the one that's 1.9, 2.9? I think that's going to be 1.9, isn't it? Yeah, and so when you get electronegativities that are, when you get this number that's 2 or approaching it, it's going to be very, very electronegative. And it's going to be polar. And we've got this chart here. I just had to run over and grab it. So we've got our electronegativity chart. We're not going to expect you to have the electronegativities memorized, but you're going to have to remember for this chart that when you subtract the electronegativities from 0 to 0.4, it's going to be nonpolar. I mean, this is like one of the few things you're going to have to memorize. Everything else on this you can reason out and figure out with the periodic table. If you get a number about 1, that's going to be a polar covalent bond. And if you get a number greater than or equal to 2, it's going to be ionic. So there we go. That's how you can predict whether you're going to have an ionic bond or a covalent bond, and whether the covalent bond will have this polar nature. Again, that's where it tends to be like a positive and negative end. And let's see, what's the chemical formula when calcium bonds with oxygen? Well, calcium is a metal. When it ionizes, it has a +2 charge because it's given up 2 electrons. And then oxygen is a nonmetal. When it needs to gain 2 electrons. So their oxidation numbers, their ionic charges, they're perfectly balanced for each other. You just need 1 calcium to perfectly balance out the oxygen over there. Now, if you were to do the crisscross method on this, you would end up with Ca2O2 if we crisscross those. But what our rule is with when you are figuring out the molecular formulas for elements, if we can divide those numbers and reduce them, we do. And those will both reduce to Ca1O1, and so we draw it like that. Covalent molecules versus ionic molecules. I'll list those characteristics. Well, let's see now. Covalent molecules, they can be gas or liquids at room temperature, where ionic molecules, they're going to be solids at room temperature. Covalent molecules are poor electricity conductors, so I'm just going to say poor conductors, where ionic compounds, when they're dissolved or melted, they are good conductors of electricity. And let's see, ionic compounds, they have high melting points. That means you've got to add a lot of energy to them before they'll begin to melt. Where covalent molecules, they have a low melting point. You heat them up, they'll begin to melt. In fact, some cases they'll just start burning right away. But low melting point. There. Okay, here's the end of page 2. Stop this.